You have been reading about dielectrics, and you notice that a new symbol, kappa, is suddenly appearing in all of your equations. So the question is, where does kappa come from? It's really kind of a cool story, but it can be a little tricky, so I wanted to go over this. You have your capacitor plates, and across your capacitor plates you have shown some charge and a charge density. The charge density is sigma. What's the electric field? The electric field is sigma naught over epsilon naught. Now we have a dielectric in between the capacitor plates. It's insulating, but charge is induced in the dielectric. There's a little bit of negative charge on the top and a little bit of positive charge on the bottom. There's a new field now inside the dielectric due to that induced charge. And if the charge density is sigma 1, the induced charge density is sigma 1, then the new electric field, E1, will be sigma 1 over E naught. Now we are going to make a not so obvious assumption that the induced charge in the dielectric will be always proportional to the surface charge on the capacitor. And it kind of makes sense if you think about it, because if you have a lot more charge on your capacitor, then you're probably going to be inducing a little bit extra more charge in your dielectric. So even though it's not obvious, it should kind of... Let's write out the total electric field. It's the sum of the external electric field across the capacitor plates minus the induced electric field, because the direction of the electric field is opposing. If we type in the values for E naught and E1, we can now substitute for E1 in order to get sigma naught over epsilon alpha, and then notice that we can pull out sigma naught and epsilon naught, and now what we have is sigma naught over epsilon naught times 1 minus 1 over alpha, and what we have is sigma naught over epsilon naught, the original electric field, multiplied by 1 minus 1 over alpha, which is just a constant. If we write this out and replace the constant by 1 over kappa, that simplifies the equation, and we notice that now the actual electric field, total electric field, is just the original electric field without the dielectric divided by kappa, which we call the dielectric constant, which is a lot easier to work with than 1 minus 1 over this proportionality constant. So that's the story of the dielectric constant. It allows us to calculate the electric field inside a dielectric without having to worry about how much charge is actually induced. The only thing we have to do is scale the original electric field without the dielectric constant by the number kappa.